Today talk will be delivered by Anastasiia Hrabovets and devoted to stochastic calculus for Bernoulli noise. Please.
Thank you. You can see now my board, right?
Mm-hmm.
Okay, so thank you for the invitation. The topic of my speech is operators of second quantization for Bernoulli noise. It is known that normalized sums of independent Bernoulli random variables weakly converge to the standard Gaussian random variable according to the central limit theorem. Moreover, for any continuous function, the following sum will weakly converge to the stochastic integral. So similarly to Gaussian white noise in L2, we can construct a Bernoulli noise in the space of continuous functions. What is already known about such normalized sums? It was investigated in the surveys of Nikolai Privot, and the surveys presented the construction of basic operators and the proof of the logarithmic Sobolev inequality for Bernoulli measures. In Bobkov's article, the study of concentration property for such sum was used to derive an almost reversion of the central limit theorem. Bernoulli noise also arises and used to prove the convergence of random function series. And in my work, I proposed the method for calculating mathematical expectation of the products of functionals from Bernoulli noise using diagrams similar to Feynman diagrams in Gaussian case. So now let's talk about the operators of second quantization, firstly for the Gaussian case. Suppose H is a separable Hilbert space, and Xi is the generalized Gaussian random element in H with zero mean and identical covariation. If the random variable alpha is measurable with respect to Xi and has finite second moment, then alpha has an Ito-Wiener expansion of the following form, where AK from Xi is infinite dimensional Hermite polynomial from Xi corresponding to K linear symmetric Hilbert-Schmidt form on H. In terms of such expansion, we can define the operator of second quantization. So for C, continuous linear operator in H with a norm less or equal than 1, the operator of second quantization corresponding to C is defined by the following formula. And I want to tell you about the representation of operators of second quantization as a mathematical expectation, because it will be useful for constructing analogs for Bernoulli noise. So consider the new generalized Gaussian random element in H, eta, of the following form, where Xi prime and Xi are independent Gaussian random elements in H with zero mean and identical covariation. Then for any variable alpha, which has an Ito-Wiener expansion, we will define a new random variable alpha from eta as a sum of AK from eta. And the following lemma proposed by Dorogovtsov states that for any measurable alpha and any linear continuous operator on H with norm less or equals than 1, the operator of second quantization related to this operator C can be represented as a conditional mathematical expectation of alpha eta with respect to Xi. And we will use this representation to construct the similar operator in Bernoulli case. Now let's talk about Bernoulli noise. Suppose that epsilon n is a sequence of independent random variables with Bernoulli distribution. And for any continuous function, we define variable phi from f of the following form, and we will call a set of such random variables by the Bernoulli noise in space of continuous functions. Bernoulli noise was constructed as an approximation of Gaussian white noise. So, and the following theorem shows the convergence of element of Bernoulli noise to the corresponding element of Gaussian white noise. This theorem can be proved by using the method of characteristic functions. And similarly to the previous theorem, it can be shown that it's also true for the vectors of such random elements, not only for the one. Sorry? Okay. It is known that in Gaussian case, infinite-dimensional Hermite polynomials are the system of orthogonal polynomials, and they're used to build a basis in space of square integrable functionals from Gaussian white noise. And now let's build a system of orthogonal polynomials in Bernoulli case. So let's define the following polynomials. A small remark here. I will use this notation with this coefficient 1 divided by n and the value of some function, because it's useful for proving the convergence to Gaussian case, but in general, we can just put here some coefficients a, I1, ik. So the lemma states that such system is a system of orthogonal polynomials, and it can be proved by using the orthogonality of independent Bernoulli random variables. We expect the objects for Bernoulli case to converge to the corresponding object in Gaussian case. And this theorem says that our polynomial akn will converge to the f from psi, which is my polynomial related to function f.
Anastasiia, could you please repeat? So they are orthogonal for?
Yeah, they're orthogonal. So if
f is a given function, then n is fixed.
Yes. And if we have the
I see. The partition is k over n.
Yeah.
Thank you.
So the following theorem states that such polynomials will converge to the corresponding Hermite polynomials in Gaussian case. And let me give an idea of the proof. We can actually prove the strongest statement, and we'll use the method of mathematical induction to prove the convergence of finite sets of polynomials of such forms. For a case where k equals to 1, we already talked about convergence. This is just an element of Bernoulli noise, and this element converges to the corresponding element of Gaussian white noise. And also because of the remark, we can say that it's also true for any vector. Now, suppose that for any length of the vector, for any decrease of the polynomials smaller or equal than k minus 1, and for any continuous functions, the following statements holds. So the vectors of polynomials in Bernoulli case will converge to the vectors of Hermite polynomials in Gaussian case.
And Hermite polynomial related to f is like a multiple linear integral.
Yes.
So thank you.
Yeah. So now suppose that we have f from c from 0, 1 to the power k, and it's represented as a linear combination of function psi m, and this is an orthonormal basis in L2, where for any m, psi m is a continuous function. Then our polynomial a kn can be written in the following form. And what I want to do is to factor out this function and this epsilon related to index k. If we do that, we will have such an expression. So we factor out this thing from the sum, and this is what's left. But in our case, these indices ik must not be equal to any of these indexes here. So we need to subtract an expression where we take into account that this index can be equal to some of them. If we look at this first expression, this expression here will convert to the corresponding element of Gaussian white noise. And this expression here, the second part, will correspond to, will convert to the corresponding Hermite polynomial because of the induction assumption. So the first term converts to the following expression. Now let's look at the second term, and I want to factor out the expressions corresponding to indices index j. So this function here, and we can see that this function again in the point ij divided by n. So we factor out this expression too. And again, we've got this expression here, and we need to subtract one more expression because this index ij can be equal to some of these indices here, and we cannot, it's not allowed here. Again, if we look at the first expression, this sum here will convert to the integral or simply an inner product in space L2 when n goes to infinity, and this expression here will convert to the corresponding Hermite polynomial of the degree k minus 2, because this hat here means actually that we remove this expression from the product. If we repeat this procedure by factoring out the indices from the sum, we will get that this expression here will convert to 0 because of this coefficient right here. So we get that this whole expression will convert to the following expression. And if we put it all together, we've got that our polynomial akn will converge to such thing, which is by definition equals to its Hermite polynomial from related to function f. About the vectors convergence, the weak limit of such polynomials coincides with the weak limit of the following form, and we can see here polynomials only degree smaller than k, so the convergence of such vector follows from the induction assumption. So we proved that orthogonal polynomials we proposed converge to the corresponding Hermite polynomials in Gaussian case. And now let's talk about chaotic representation for functionals from Bernoulli noise. Consider an arbitrary function from one Bernoulli random variable. Such function must be uniquely determined by its values at points epsilon equals -1 and epsilon equals +1. Therefore, such function is linear and can be represented in the following form. Now, suppose that for an arbitrary function from n-1 independent Bernoulli random variables, this function can be represented as a sum of orthogonal polynomials, which we described before. So we can rewrite it as the following form. Now, if we for any function from an independent random variable, we can represent it, we can fix value of epsilon n. For example, if epsilon n equals to -1, then the value of function fn equals to the value of some function fn -1 -1. And the same for the case when epsilon n equals to +1. So again, this function fn can be represented as a linear function from variable epsilon n, but the coefficients will depend on these functions fn -1 and n -1 and fn -1 +1. So And as we talked before, such functions can be represented as a sum of orthogonal polynomials. So for any function from n Bernoulli random variable, we've got the following representation. And now let's use such a representation to propose a definition for operators of second quantization. In Gaussian case, as I said before, the operators of second quantization are defined as conditional mathematical expectation. And we will use the same approach to construct similar operators for Bernoulli case. We will define a new sequence of independent random variables with the following distribution. So you can see it here. And note that epsilon n prime, again, Bernoulli random variable. Now, the following lemma states that conditional expectation of product of such new random variables equals to the following expression: epsilon I1, P I1, epsilon ik, P ik. So for any alpha measurable with respect to our initial sequence epsilon, this alpha has the following representation, as we've talked before, and we will consider a new random variable alpha from epsilon prime, and we basically just substitute epsilons with our new random variables. If we calculate the mathematical expectation of such new random variable with respect to epsilon, we've got the following expression. So let's define the operator of second quantization corresponding to the sequence Pn as follows. So gamma from P x on alpha will be equal to the following sum. Representation as a conditional expectation give us some good properties. For example, as I said, this new random variables, again, Bernoulli random variables. So if alpha is, for example, non-negative, then its conditional expectation will also be non-negative. So we can say that operator of second quantization will keep the positivity of function. Now let's move to the Ornstein-Uhlenbeck semigroup operators. Ornstein-Uhlenbeck semigroup operators, they are partial case of operators of second quantization, and they have a number of useful properties. They're used, for example, to localize and extend a stochastic integral, as in a work of Berukhov and Gumilkov. In the Gaussian case, in terms of Ito-Wiener expansion, the operators of Ornstein-Uhlenbeck semigroup are defined as follows. And we can easily define the similar operators for Bernoulli case using our definition of operator of second quantization. We just put for any n, Pn equals to the constant exponent to the power minus t, and the corresponding operator of second quantization will be equal to the following expression. And it has some good properties. For example, it converts to the corresponding operators in Gaussian case. To understand this, we can look at its action on the our polynomial a kn. So we just multiplied every function by exponent to the power minus t. So we've got the following expression. The semigroup property, so if we act with the operator corresponding to time s, and then we will act with the operator corresponding to time t, we've got the action of an operator corresponding to time t plus s. Operator of Ornstein-Uhlenbeck semigroup, it's actually a contraction operator. If we calculate the square of norm of such of T alpha, it equals to the following expectation, and because of the orthogonality of Bernoulli random variables, is equal to the following series, and this is less or equal than the squared norm of alpha, which is this series without this exponents. We just sum of coefficients squared. And strong continuity. Again, we will calculate the following expectation. And when t goes to 0, such expression goes to 0 as well. Now let's note an interesting thing. We can, when we define the operator of second quantization in Gaussian case, we defined it for any continuous linear operator on H. And we want our definition for Gaussian or for Bernoulli case. We want to get, again, operator corresponding to any operator on the space of functions. And if we construct a sequence Pn as the values of some continuous function, and we will act again on our polynomial, it was already proved that this polynomial converges to the corresponding Hermite polynomial. And if we act with the operator of second quantization on this polynomial, we will get the following expression. So we just multiplied it by the function j. So what we've got, in the limit, we obtain the operator of second quantization corresponding to multiplication operators. We need to offer a more general definition for operators of second quantization for Bernoulli noise. And this is what I'm working on right now. But for today, that's all. Thank you for your attention.
Okay, thank you for the presentation. And before we go to the discussion, I must say that here in the proof of theorem, there is a lot of technical work. So Nastya only presented the formulation and main idea of the theorem about convergence. And the interesting question can be discussed relatively to Röhrstein-Uhlenbeck semigroup, because if we consider, for example, finite dimensional Hilbert space H and Gaussian noise in this space, in this case, this is simply Gaussian random vector, then still Röhrstein-Uhlenbeck semigroup can be defined, and it is Markovian semigroup. It is related to well-known Röhrstein-Uhlenbeck process. Such construction cannot be applied to infinitely dimensional case, but still due to this effect, in infinitely dimensional case, Röhrstein-Uhlenbeck semigroup has a lot of good properties in Gaussian case, for example, hypercontractivity and so on. From this point of view, it was interesting to understand, has the Röhrstein-Uhlenbeck semigroup in Bernoulli case such Markovian nature or not? And recently I got positive answer on this question. So let me demonstrate a screen and to show you what happened. Okay, here is my screen, and let me find it. Okay, here is it. Okay, and then. Let me find it. This file. Okay. Okay. So what is the main question? We already know that if we consider Bernoulli sequence, then any random variable which is measured with respect to this sequence and square integrable can be uniquely represented as a following sum of multiple sums. Then we defined Ornstein-Uhlenbeck semigroup exactly as in Gaussian case as follows. We just multiply and sum on e on exponent with minus nt. The main question is the following: is this semigroup of Köthen-Markov process? And where this Markov process live? So let me present you construction. Let us start with our space of sequences. I will denote it by K. K is the space of all sequences with elements -1 and 1. The distance in this space, let us define as such sum from n1 to infinity 1 over 2n xn minus yn. With such distance, it becomes to be compact. And now consider m infinity. It will be a set of all product measures on K. Namely, each element here is not only probability measure on K, but it is a product measure. So one can consider it like a distribution of the sequence of independent -1 + 1, but with different probabilities. Then on M infinity, one can define topology of weak convergence, and it is also good space. Now let us define dynamics in this M infinity. Suppose that tau n be independent exponentially distributed random variables with lambda equal to 1. Take m, take mu, which belong to M infinity, and define process mu t as follows. Mu t at every moment t will be a product measure, but random. If tau n is greater than t, then mu nt is equal initial mu n 0, those measures from which we started with this coordinate. And if tau n is less or equal than t, then mu t is just uniform distribution. So it is just Bernoulli distribution. Now let us see the properties of obtained measure-valued processes. Of course, it is Markov process because its coordinates are Markovian and move independently due to independency of tau n. Consider now a function f from k to r. I will write this function in representation which we already discussed. I suppose that coefficients a converge to 0 in such a manner that this series converge for any x from k without any problem. Then for such f, one can take the integral with respect to our measure-valued process. I will denote it by brackets. This is simply integral f against measure mu t. Then the elements of k also can be identified with the measure. If x is a sequence, then it can be identified with the measure delta x, which is just a product delta x1, delta x2, and so on. Then the following formula holds. If we consider the expectation of our integral f with respect to measure mu t, starting from the point x, from delta x, then we will get the following representation, which we already face in definition of Ornstein-Uhlenbeck semigroup. Why it is true? It is not too hard to understand, because in order to remains value of x in such products, x I1 and so on, x en, we need that the corresponding exponential time is greater than t. They are independent, so this multiplier e minus nt arise. In opposite case, what we will have? In opposite case, we have just uniform distribution. And we know that it has zero mean. And they are independent because we consider product measures. So the integral with respect to this uniform distribution of corresponding coordinate will be equal to 0, and it kills corresponding multipliers. So in this way, we understand that proposed Ornstein-Uhlenbeck semigroup is really a semigroup of Markov related to Markov process, but Markov process on the space of measures on our sequences. This was a remark which I wanted to show you. Thank you. Maybe somebody have questions or comments, please.
May I ask a few questions?
Yes.
Andrei Anatolich, first of all, regarding your remark, the model which you consider somehow in style is similar to the simple symmetric exclusion process. At least the state space is similar, and the dynamics is slightly different. But in simple symmetric exclusion process, the invariant measure also is a Bernoulli measure. And in that case, actually, people work with that process as follows. So one can identify the simple symmetric exclusion process with a measure on the say a positive part of the line, where you just put masses at points k over n, where the mass is equal to 0 or 1 depending on the values of the simple symmetric exclusion process. And then one can show that under the scaling limit one can go to the solution to the heat equation, or one can also consider the fluctuations around the average, and then you have the conversion to the generalized simple to the generalized Ornstein-Uhlenbeck process, and so on. But in that case, you have that kind of identification that you just consider the measure on the space, say R, or a half line if you consider points at integer and at natural numbers. And then you consider, and after that you write the dynamics, how it looks like, you test by cylindrical functions and so on. So here you consider slightly different functions than cylindrical functions. Is here any advantage that you work in this way, but not in the way how usually people work with the simple symmetric exclusion process?
You know, I just constructed this object, but I think that it is rich because, of course, this is only simple example of dynamics on this product measures. So I think that with the help of this idea, we will construct different Markov measure-valued processes, and then let's see, maybe we will use it in investigation of Ornstein-Uhlenbeck semigroup, because such representation work well when we, for example, when we discuss in Hauschian case Sobolev concentration inequality, then one of the nicest proof I found in Bogachev book devoted to Hauschian measures, and it used exactly representation of Ornstein-Uhlenbeck as a Markov semigroup. So I think that this dynamics will be useful for us. And because of I constructed it by hands, I didn't think about comparison with the existing models, despite of the book of Liggett on the interacting particle system. Because actually this is simplest model which is closely related to Ising. And I think we will use this Ising idea and we will construct much more dynamics. Maybe then I will need additional technique and something like general space of measures and so on.
It would be interesting to see what is the scaling limit and also what is fluctuations around scaling limit. So this topic is well developed, and in particular here, if it was not done before, then I think it would be really interesting. And
yes, you know, this measurable process actually, where it lives on the space for infinitely dimensional Ehrenfest model. Yes, because this is K, it is an infinitely dimensional cube, and we can consider the motion and Bernoulli distribution is invariant distribution for the Ehrenfest motion. And there is the so-called cutoff effect when we trying to start from arbitrary distribution and measure the distance to uniform of Bernoulli distribution on the cube. And it occurs that it heavily depends number of steps heavily depends on the dimension of the cube. So in infinite dimensional case, it is new. And I think we will go in this direction.
Okay, thank you.
Okay.
May also the second question very quickly, probably to Anastasiia. Your first part of the talk, where you talk, as I understood, about some kind, I mean, the central limit theorem, if I remember correctly. Did you also consider the rate of convergence? So how fast do you have the convergence to the limited object?
I didn't think about that. This theorem I proposed, it can be proved by using the method of characteristic function, and I don't actually think about the speed of convergence.
Okay, because as I understand, in the limit you get some kind of Gaussian object, and therefore here should work nicely multidimensional Stein method, which is already developed in the general case, and everything what you need to do just check the conditions there. But as I remember correctly, there you will need additional assumptions that function f has to be smooth, probably has differentiable up to the third derivative, and then you can say something about how fast or what is the rate of convergence. Here, as I understand, you don't have any assumptions on the regularity of function f, only continuity, right? So therefore, so you have more, but you cannot say about the speed of convergence, right?
Yeah, but thank you. I will think about that.
Yes, it is a rich object which we began to study with Nastya. And I must say that in the article of Bobkov, which Nastya mentioned, he studied speed of convergence using concentration inequality for Bernoulli random variables. So some assumption is done in this direction.
Okay, thank you.
I have few questions, and one is, okay, it is not question, but comment that epsilon squared is 1. So that's why this orthogonal polynomials have very simple structure. But you see, and now let's consider, let's recall Donsker theorem, that if you construct a sum of these epsilons, and if you scale, then you have a Brownian motion in a limit. Is it possible to deduce these results on convergence to multiple linear integrals from Donskoy's theorem? Maybe for smooth at first, for smooth functions, you may even integrate by parts. And if f is smooth, then integral of f dw is integral. So you integrate by parts, and you have w df, and this is continuous functional. Maybe the same for multiple.
There are few remarks here. One is the following: that if we will consider arbitrary random variable, even centered, then it is not clear that we will have such nice orthogonal polynomial representation. We will have only, this is U statistic. This is U statistic, actually. And for U statistics, I have already results about convergence to multilinear linear integral. In my book, Stochastic Analysis and Random Maps in Hilbert Space, it was proved. But only for one, and I consider it slightly different situation from a Nastya case. But it is put. So this is one, and another one that we intend that we are studying right now Bernoulli variables because of the good algebraic structure. Maybe you remember Nastya talked about the analog of Feynman diagrams. It was very nice that we can get some good algebraic structure which goes to Gaussian structure. So this was a reason why we concentrated on such small random variables.
And another question is the following. So if we consider cylindrical Gaussian random element in a Hilbert space, and if you take, say, nuclear operator and act, you will get usual random variable. Is it possible to prove some kind of convergence of this Bernoulli noise to Gaussian noise in such a way that if you have nice operator, then you will get
I think yes. I think yes. At least it is very reasonable.
Okay, thank you.
I have a comment or a question. It is related to the second remark of Vitaly. If you consider this, if you want to speak about the rate of convergence to the iterated eta-Wiener integrals, it seems that we have the same distribution as in the case if we consider general, the Gaussian case, or not.
What do you mean the same distribution? Multiple integral has another distribution than simple.
Oh, you have Gaussian in that case. Okay, yeah, I see. Thank you.
Okay, some other questions, please?
Yes, I have one comment that Nastya mentioned Nicolas Privot. So he has a book about stochastic analysis in discrete and continuous setting, and in discrete setting he does a lot of not for necessarily independent increments. He works with the increments that are so-called normal martingales. These are like martingale differences, but also with an assumption on the square of them. So maybe, and there he develops in multiple stochastic integrals in discrete setting and so on. And maybe a lot of can be extended.
Yes, but still I am insisting that we are concentrating on this Bernoulli case due to its very nice algebraic structure. So we are not only interested in to get some approximation to Gaussian, to get some limits here, but we are interested in studying of this rich object itself. As I said, For example, in Ehrenfest model, this cutoff effect is not very old thing. It was discovered like in beginning of this century. So we have a hope that this nice algebraic structure, together with the analytic, will give us interesting result exactly about this distribution.
Okay, thank you.
Okay, if there are no other questions, I don't know who will be next speaker.
Next speaker will be Mykola Vovchansky.
Okay. So for today we finished our work. Thank you, thanks everybody for discussions, and see you next week. Bye.
Thank you.
Bye bye.
Bye.
Thank you. Bye.
Thank you. Bye.